If you recall, we've been talking about the calculus things, derivatives and integrals. Derivatives tell us about in the single variable calculus, the derivative tells us the slope of the line tangent to a function at a point, and integrals tell us area under a curve and above an interval. And we want to look at this derivative business a little bit closer, because we need to just update what we know about derivatives and integrals to cover functions of more than one variable and eventually equations of more than two variables, be they functions or not. And this is what we want to start with. We want to recall that the derivative of a function tells us the slope of the line tangent to the function at that point. And we want to interpret this slope as an indication of the direction that the line is headed. Slope is rise over run, so it's really built out of two things. We always think of the slope as one number. We interpret it as the instantaneous rate of change, but it's always made up of two things when we think of it as a direction, a rise and a run. So when we have a line, the reason that lines are so simple is that the ratio of the rise to the run is constant between any 2 points. So between, say, point 1 and point 2, we have a rise and a run. Because we only have two, we decided let's make a ratio out of them. That will tell us how much the function goes up when x increases by 1. That'll tell us how much y changes when x increases by 1. This will be convenient. It takes those two directions. Since that ratio is always the same, it's a way of describing two numbers with one number. It's nice and efficient. I said we like I was there. So it still works in our other context, instantaneous rate of change. But today we want to think of it as direction. Here's why we want to think of it in terms of direction. When we looked at a function of two variables, we saw a function changing when x increases, and we saw the function changing when y increases. We've established two directions. Instead of just having x increasing by 1, we're going to want to know what happens when y increases by 1. So that's where our upgrade is going to have to come from. For functions of two variables, we're going to see changes in two directions. X can change and y can change. It's actually more than two, but we're going to focus on what happens when x changes and what happens when y changes. Because really, we've got 360 degrees around any points in the xy plane that we can pick for a direction. But we're going to focus on x and y because any one of those ones in the middle is going to be some combination of x and y directions. So we want to make a note, really, 360 degrees of direction to choose from. So really, we're going to have 360 degrees of direction to choose from, but all those directions are going to be combinations of some x and some y. For functions of one variable, life is very boring. X can increase by 1. And it's just a ratio after that. But for functions of 2 variables, we don't have a curve, a one-dimensional curve in 2-dimensional space. We've got a 2-dimensional surface hanging out in 3-dimensional space. So if we're standing on a point, we can't just go positive X direction, positive Y direction. If we're standing on a surface, we can go positive X direction, negative X direction, positive Y direction, negative Y direction. We've got these 2 directions to go and everything in between. So I could do some combination, 1 step in the X direction and 2 steps in the Y direction. Every direction in the XY plane is some combination of X and Y. We've seen this happen before. That's why we need 2 coordinates to describe the plane. Because there's horizontal stuff and vertical stuff. So we really get 360 degrees of direction to choose from, but these are all going to be combinations of these 2 directions, X and Y. We need a way to sort this out. So we need a way to describe X and Y directions at the same time. Saw this a little bit last week when we talked about delta Z over delta X. How much is Z changing in the X direction? And delta Z over delta Y. How much is Z changing in the Y direction? We're still just trying to expand our slope of the tangent line. But now if we're making a tangent at a surface, I have some slope in the X direction and some slope in the Y direction. Got to be able to sort all those things out. Any questions? So here's what we need to bring up. Our next important tool for describing stuff. Okay. A vector describes a quantity with magnitude and direction. This is different than our real numbers. In this context, we'll start describing our real numbers as scalars. They only have magnitude. For our purposes, scalars are going to be real numbers. So for us, the scalars are going to be real numbers. All we really need is a field, but that's more general. So we're gonna have two different kinds of quantities, vectors and scaling. You've been through physics, same vectors we were talking about then. If you've been through linear algebra, same vectors we were talking about then. If you've been in engineering statics, same vectors we've been talking about then. If you're like, oh man, does this vector stuff ever stop? I don't know. Probably not. We live in a three-dimensional world. We can't just describe direction with one number, rise over run, for the rest of our lives. I guess we could just work to make the world two-dimensional. But there are numerous experiments that are up on the YouTube showing that it is three-dimensional and it's round. You know what I'm talking about? There are people that still believe that the Earth is flat. Then they make an experiment to prove that the Earth is flat. Their experiment indicates that the Earth is, in fact, round. They're like, oh, something must have gone wrong. And they go, well, yeah, something went wrong. The Earth is round. You keep proving it to yourself. Incidentally, for those of you who grew up in America, I don't know if they teach you this anymore, but when Columbus took off, if you believe that the Earth was flat in 1492, you were just as crazy then as you were now. It wasn't like a widespread belief, or it wasn't any more widespread than it is now. You were just as ignorant then as you would be now, if you're like, all the Earth is flat. Probably a lot of people were cheating, like modern scholars would be cheating, because a lot of people just wouldn't even have time to think about that. They don't have time to think about the shape of the Earth because they're more concerned with like growing crops for their lord so they don't get kicked off their land. God, we haven't come very far, have we? You're like, oh, it's a good thing we got rid of that fuel system. Oh, dang, I'm late for work. I better get going. Hang on a second. I want to go back to that first thing you said. Yeah, it might get fired. Then I'll be homeless. All right, when you get back, I have some words about the free market. Free market, woo! You know what I mean? Anyway, what are we talking about? Vector. So, let's talk about vectors. In vectors, we're going to go right back to what I described here. Here's where I first started describing vectors. We've got 360 degrees of direction to describe, but they're all going to be combinations of X and Y. Those of you who've been through linear algebra are like, oh man, why do you got to restrict us to just X and Y? Why do they have to be the same length and perpendicular to each other? Because that's easiest. But it could really be any couple of directions that we want. But we definitely need two of them. So every direction in the XY plane is going to be described with an X and a Y coordinate. So we're going to have a vector. We're going to represent vectors with arrows because they have magnitude and direction. The magnitude is going to be the length of the vector, and the direction is the direction that the arrow is pointing. So the magnitude is going to be represented with the length, and the direction is just the direction. We're going to give our vectors names. But we want to make sure that when we're reading about vectors, since we're giving them very simple names, just single letters, is how I'm going to name my kids if I ever have kids. First kid, A. Second kid, B. Third kid, D. We don't talk about C. And people would be like, oh, why just one letter? And they're like, oh, why'd you give your kids so many letters for their names? That seems complicated. Be trouble if I have twins. Actually, wouldn't be no trouble at all. I just use subscripts. X1 and X2. No trouble at all. Now, this may seem cruel because it is. Because the names that you give to your kids, it's going to be like the first line of attack that their schoolmates will have on them, right? That's like the first thing they go after. For me, it happened in 7th grade. My last name is Leach. It is one letter away from the flatworms. And its origin is the flatworm anyway. Because apparently in my family's history, someone was like a barber. And you would go in and say, oh, I have bad humors. And I was like, oh, well, let me get the jar. And I'd put, then my ancestors would put leeches all over somebody. They would sit there and suck the blood out for a while, pull the leeches off. Well, off you go. Medicine. Come from a long line of doctors, apparently. What are we talking about? Oh, yes. And then the spelling got changed because English. We're going to give our vectors names, but when we're writing them, we need to distinguish between vectors. So we'll use a letter, and then we'll put an arrow over the top of it to indicate that we are talking about a vector. So the arrow is going to be our notation for a vector. So if we drop an arrow over the letter name, that'll indicate a vector. If we're typing, we might use boldface. So a common strategy is just to use boldface for typing vector names, because you still want to distinguish them between vectors and scalars. Any questions? How's everybody? Okay. Of course, we're just naming parts. Yes. A scalar will just be a number. So we need to talk about how we're going to describe vectors. And we have lots of ways to describe vectors. So here's going to be a vector v. We're going to describe vectors by imagining a coordinates, imagining them sitting on a coordinate system. So we're going to imagine a coordinate system. Every single time I make the x-axis the same length as my vector in the horizontal direction. And I know I've got to drop the vector down to the x-axis. And then I just forget to leave space. So I've got this vector. I'm going to imagine the starting point of the vector sitting at the origin. And I'm going to have an x and y coordinate system superimposed on top. And then I can just describe this vector with components. a horizontal and vertical component. So we'll describe our vectors with horizontal and vertical components. Break them down into two pieces. Like I said before, we've got 360 degrees of choice, and we're going to write all those in terms of these two, horizontal and vertical. So if I put an origin at one end, at the tail of the vector, then the coordinates at the other end of the vector will describe the horizontal and vertical components. So this vector might be the vector 5, 3. So if I've gone from one end of the vector horizontally 5 units long and vertically it's 3 units long, I'll call this vector 5, 3. One of the common ways to indicate a vector, horizontal and vertical components, to distinguish it from just a point in space, is put the pointy brackets on, the low res parentheses. One way to indicate that we're talking about vectors is to put them in pointy brackets, so list the horizontal and vertical components. Unfortunately for our heroes, sometimes we are talking about a vector and we just put it in parentheses. Jerk move on our part, I know. You'll just have to know that we're talking about a vector and not a scalar. So it's going to have to be clear from context. I'm imagining this was originally what was going on. It's like, oh, well, we'll just describe the end point. Well, it says 0, 0 to this point. And someone's like, oh, that's awful. We're already using that for coordinates. Someone's like, oh, well, they're kind of coordinates. And then someone else is like, oh, we're also using that for interval notation. And everybody's like, oh, it'll be fine. And then Morgan Freeman would be like, oh, it was not fine. So sometimes we get lazy about our pointy brackets. Yes. No, the magnitude will be the length. A scalar just is, its magnitude is just its value. So if a scalar is 4, its magnitude is 4. If a scalar is, the scalar -7 has a magnitude of 7. That's the length of that. Yeah. Doesn't have to be. So we're going to when we're describing vectors, we always imagine the starting point to be at the origin to come up with these coordinates. So if I take a vector and draw it way the heck over here, right? It's still going to have horizontal and vertical components, and I'm going to imagine my origin at the end of that vector. So in the same world, I've got a vector over here. And so to describe that, I just go to the starting point of this vector and I grab my coordinate system and I kind of slide it over here. And then use that to describe this direction, with the understanding that both of these vectors are using the same orientation, horizontal and vertical. So this vector looks like it's going to be -1 in the x direction and 3 in the y direction. Any other question? All right. How many of you have seen vectors before? The rest of you probably just don't. That was pretty good. That was actually a lot of people actually raise their hands. A lot of times I can be like, oh, raise your hand if you know what 2 + 3 is equal to. Only like 2 people. Wow, seriously? Are we gonna go back that far? But if I ask anti-question, raise your hand if you don't know it. Then everybody's like, oh, everybody who knows 2 + 3 is like, oh, well, I don't have to raise my hand. Plus, we tend to get embarrassed by things we don't know for no reason at all. Right? Like you take a calculus test or something like that and you miss some questions and you're like, oh man, I missed these questions. Like, oh, you're supposed to miss questions. That's like the whole point of having the questions. You know what I mean? But then teachers like make you feel bad about it. Dick move on the teacher's part. Don't make people feel bad about things that they didn't get right. I mean, that's why you're here. You know what I mean? That's like the whole point. Messing stuff up. So that's how we learn. That's also known as the Joker test. It's someone in a Calc 3 class. I'm like, oh, raise your hand if you don't know what 2 + 3 is. You're like, oh, I don't know what 2 + 3 is. But then I'm like, oh, get out. I go, what? You're clearly unqualified for this class if you don't know the basic facts of arithmetic. You need to go find another class. So I go, no, just get out. I'm just kidding. I just secretly drop them off of the roster on WebSmart. Make them do the whole class. I go, oh yeah, I threw you out of class 16 weeks ago. Just kidding. Although sometimes, this is why it's difficult to drop students. Sometimes a student will disappear for a month. It's like, oh, they must have dropped. I'm going to drop them so they don't get a failing grade or something like that. So I drop them, and then the next day they just like show up. I'm like, oh, where have you been for the last month? No, you stopped passing your attendance sheet around, so I didn't think you were noticing. Well, all right, have a seat. I don't tell them that I dropped them. Show up for the final. Well, who are you? I'm here for the final. No, you're not. I'm just kidding. Oh, I just tell them, you need to get yourself back into this class. Anyway, so we have a direction. We're describing that direction with coordinates. We're going to imagine one end of the vector is at the origin, and then the other end of the vector is at some coordinates, with the understanding that at the tail end of this vector, there's a horizontal x-axis and a vertical y-axis. And we're just always going to agree x horizontal, y vertical. Otherwise, it wouldn't mean anything if over here, my x-axis was all wonky like this, and I was using different x-axes all over the place. That's not going to work. So we're just always going to make horizontal and vertical. That's how we're describing the direction. If we want the magnitude of the vector, I just want to use the length of the vector. So magnitude is length. So if I have this vector v, 5, 3, and I want to know the length of the vector, I could just use the distance formula. You can see that we're making these nice right triangles. This is why we love this so much. It's so simple. This is why we use orthonormal coordinates. But we need notation for the magnitude of the vector because this is math class and we need notation for friggin' everything. And so for magnitude of v, it's going to look like absolute value, but two of them. Double absolute values. That's the magnitude of v. It's the length of the v. This is going to be a scalar. And that is just the length of this vector. We're also going to get lazy about this one and just use our same absolute value notation. Because we don't want to write two of them all the time. Absolute value is in the same category as magnitude. It tells us the absolute value, and it's calculated in the same way. The magnitude or the absolute value of -5 is 5, not because we made it positive. We took -5, squared it, got 25, square root is 5. So that's how we make absolute values. When you're super pedantic about things, instead of just erase the negative. You get more out of it if you say it's the square root of the square to get the absolute value. Because then you note that -5 squared, the negative gets squared along with it, becomes positive 25. And then you get reminded that when you write that square root symbol, you are referring to the principal square root or the positive square root, not plus or minus. Plus or minus is something that we only have to worry about in equations when we're trying to figure out all the x's that fit a certain description. That's when you'll need things like plus and minus. You know what I mean? So when you write square root of 34, you mean the positive one. If you want them both, that's when you say, well, plus and minus. If you're like writing the solutions to x squared equals 34, plus and minus square root 34. You know what I mean? If this sounds super pedantic when we're talking about it, that's only because it is. But the magnitude is going to be the length of the vector. How's that, okay? Now that we have this, we can introduce the other way to describe vectors. Unit vectors. So unit vector just means it has a vector with a magnitude of 1. And we're going to establish two important unit vectors. One is 1 unit all x direction. 1 unit in the x direction. And we're going to have notation for that. It's going to be I with a little hat on it. I don't know who came up with this notation. It was really cute at first, but now I find it kind of annoying to be like, oh, I hat. Do it enough and you'll feel silly saying I hat, so you just say I. Then you'll be like, oh, but hang on a second, isn't I supposed to be the imaginary unit square root of -1? And I'm like, oh, quiet you, we're using it for more than one thing, which is something that we're not really trying to not do in math, but shit, we got a lot of legacy content that we have to deal with, like square roots. It's like legacy content that we're just kind of stuck with. I is the imaginary unit. I is going to be this unit vector. Why don't we just start with J? I wasn't at these meetings. This is just like legacy content that we're kind of stuck with. So I'll have this unit vector in the X direction, I hat, and we'll have a unit vector in the Y direction, J hat. Yes. Not quite. The component itself is just a scalar, but these are going to be also our components. Yeah, we're just getting one direction. So we'll have a horizontal component counting how many i's we need, and then a vertical component, how many j's we need. So we can describe that vector v . We're going to describe this as 5i and 3j. I'm already not drawing paths. This is why we're using these components. This is why we use these coordinates. It's really easy to find these locations. This is also really good because it displays very clearly very efficiently, how scalars interact with vectors and what a linear combination is. This 5i plus 3j is a linear combination. Linear combination means we're making a combination with scalar multiples, scalar multiplication, and addition. We're just using scalar multiplication and addition. So this is going to be 5 scalar multiples of 1, 0 plus 3 times 0, 1. Scalar multiplication, vector addition. Those are two operations that are in play here. Last thing today, set your Wayback Machine to trigonometry, because we have another way of describing directions. Earlier, I said there are 360 degrees we have to choose from, and we're going to make them as combinations of x and y. We could also just make them as a magnitude and a direction described as degrees, but we have to pick a starting point. We can also describe a vector with a magnitude and an angle in standard position. Standard position is measured in degrees or radians from the positive x-axis, with counterclockwise being the positive direction. Thinking back to trigonometry, angles, an angle in standard position and a magnitude is polar coordinates. This is our project for this week, dealing with vectors. Running in the background this week is still reviewing our library of surfaces and reviewing and building our library of surfaces so we can picture some more things. This is all just working on the describe stuff portion of things so we can get to the calculus portion of events where we talk about how derivatives and integrals show up with these surfaces. Any questions? I know today was a lot of naming of parts. It's Monday. It's week 3. It's starting to set in now. Got this morning. That motivation you might have had at the beginning to be really awesome at calculus is starting to wane. And you're like, oh no, there are 15 weeks to go. Oh boy. One of them shortened by a couple of days because of Thanksgiving. So keep that in mind. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing.